And we should start. Dear all, it is a great pleasure to have with us, even though only virtually from the City of Lights, Guy Perrin, for this joint colloquium of the Department of Physics of the University of Crete and the Institute of Astrophysics of Forth. Guy Perrin has obtained his first degree from the prestigious École Polytechnique, which is located in the suburbs of Paris. And in 1997, he received his PhD in astrophysics in optical interferometry from the University of Paris number 7. He commenced his professional career as an astronomer at Paris Observatory, where he contributed to numerous advances related to state-of-the-art optical interferometry, as well as adaptive optics, including the MIDI instrument of the European Southern Observatory, in which he was co-PI. Currently, he is leading the French contribution to the new impressive optical interferometry instrument known as Gravity, which is in operation at the Very Large Telescope in Chile and already provides spectacular results. As you can imagine, Dr. Perrin is a world specialist in high angular resolution astrophysics, and his interests are in evolved stars, active galactic nuclei, and of course, the supermassive black hole, which is located at the center of our galaxy and is known as Sag-A star, since the center of our galaxy is located towards the constellation of Sagittarius. For his scientific accomplishments, Dr. Perrin has received a number of prizes and awards, including the Young Researcher Prize from the French Astronomical Society in 2005. The Institut de France awarded him the Simone and Sino del Duca Scientific Grand Prize in 2015. As a leader of his team, he received the La Recherche Prize in 2019. And most importantly, I think, since 2019, he is Chevalier of the National Order of Merit. I don't know what comes with that, but it is very important
medal
nowadays. In parallel, though, what is very impressive is that in parallel to his scientific achievements, Dr. Perrin is also finding time to contribute to the advancement of astrophysics in France and in Europe from various administrative positions. He has served as Vice President of the Scientific Council of Paris Observatory in the past, and currently he is the Deputy Scientific Director in charge of astronomy at CNRS in Seoul. The title of his colloquium today is Exploration of the Supermassive Black Hole at the Galactic Center with Gravity, and we all look forward to hearing what he has to say. Guy, the floor is yours.
Thank you very much, Vasilis, for this very nice introduction. And I have to say that I have a great pleasure to collaborate with Vasilis on various opportunities. And I've come to Forth and to Crete a few years ago for our to set up our Europeans program together. So thank you very much for the invitation. Of course, it's a pity I cannot be there with you. It would have been an even greater pleasure. But okay, that's the way it goes these days. So we are all happy to be here and to be able to talk about science. As you've seen, I have slightly changed the title of the talk. Well, it is still the same title, except that I have replaced black hole by compact object, because we don't absolutely know whether it is a black hole or something else, but clearly the black hole is the most likely explanation. I will start this talk by introducing you to our galaxy, at least what we think it looks like. There are many observations of the galaxy and characterizations of the galaxy, so we have a very good model of what it looks like. This is an artistic view of our galaxy, as if it were seen from, or as it is seen by very distant friends. You see it's a spiral galaxy with a bar in the middle. It is 25 kiloparsecs across. If you're not an astronomer, it's about 80 light years across. We are approximately here at 2/3 of a radius. That's the location of the solar system. And of course, the Galactic Center, Sagittarius A star or Sag-A star, sits exactly in the middle of the bar and in the center of the bulge, as you would see it from the top. Now, this is how we see the galaxy. we are in the plane. So when we look at the galactic center, we actually see the galaxy through the plane. And this is a very obscured region. Oh, excuse me, I went too far. I actually don't see the bottom of my slides because of the zoom bar. This is why I clicked too much. And I think at the bottom of my slide, it is written that we observe the galactic center in the IR, in the infrared. You can observe it at other wavelengths, but it's very difficult to observe it in the optical because since we see it through the galactic plane, it is very much obscured by gas and more importantly by dust. So that's why the gravity instruments observe in the near infrared to fight the very large extinction. And if you zoom in a little bit, you will see that the galactic center looks like the galactic center regions looks like a spiral galaxy, but with a spiral pattern. But that's only a chance, actually. This structure is an H2 region. You see the scale, about 1 arc minute, 50 arc seconds, or in physical scale, 2 parsecs. And these structures are more the walls of bubbles. And so this is where Sage's star sits. If you look now at stars and not at the gas like H2, what you see are stars on scales of a few arc seconds that are organized into two disks of about 100 or less than 100 massive evolved stars, OB and Wolf-Rayet stars. And now if you look at the center of this region, on a scale which is even smaller, the central arc second, then you have another cluster, the S-star cluster. It was called the S-star cluster. It's a cluster of about 50 massive main sequence stars. So they are younger than the stars of the two-disk central cluster. And this region is quite compact in the sense that you see that it is contained in a region smaller than 1 arc second. The 1 arc second is the classical limit of observation in the optical limit in angular resolution set by the turbulent atmosphere. And now, if you look at the very center, of course, you find Sage's star. So it was first discovered in the radio in the 70s, and then was later identified also as a source that could emit in other wavelength ranges, like in the infrared, as you will see later in the talk. And if Sage's star is a black hole, then we know the Schwarzschild radius because we know the mass, as you will see, and the Schwarzschild radius is on the order of 10 microarcseconds. So the Schwarzschild radius is the radius of the event horizon of the black hole in the case where the black hole is not spinning at all. So you see various angular scales here, and the ones the ones we are going to address are on the order of an arc second or less, down to a few tenths of microarc seconds. So that's a large dynamic range of angular scales. And of course, the whole goal here is to study Sage's star and try to identify the nature of this object. And it has been the quest for several people for now almost 50 years. Okay. As you will see, the black hole is important, of course, but the stars around the black hole are going to play a very important role in the rest of this talk. So we would like to see stars at the center of the galaxy, and especially the S stars. And if you look at the central parsec, and more exactly at the central arc second, in order to see individual stars, well, you need to have a sufficient angular resolution. And the angular resolution is set first by the size of the telescope you're using. It's called the diffraction limit. It scales like the reciprocal of the diameter, and it scales like the wavelength, so it's lambda over d. So the larger the telescope, the smaller the details you can see. And but so that's a way to increase angular resolution, of course. But there's also the problem of the turbulence of air, of the atmosphere, which limits the angular resolution to roughly 1 arcsecond. It depends on the quality of the site, and it depends on the time, on the moment where you observe. So for the first constraint, the diffraction limit, we have a wonderful solution in Europe, since we have 4 8-meter telescopes, and not only Europe have 8-meter telescopes, there are other 8-meter and 10-meter telescopes around the world. But we have these 4 8-meter telescopes in Chile. They are part of the European Southern Observatory. They are wonderful telescopes, but these telescopes alone are not enough if you cannot correct for turbulence. And to correct for turbulence, what you need is what is called an adaptive optics system. So what is the impact of turbulence in practice? What you see here is an optical simulation of an observation with an 8-meter telescope at 2 micron wavelength in the near infrared. I call it an optical simulation because it's real photons, but it's not stellar photons or astrophysical photons, but photons from a calibration source going through a system that mimics the effect of turbulence. So screen phases that mimic the effect of turbulence. And this is used to practice with the adaptive optics system. The big interest of that is that there's almost no noise, or the noise, let's say, is negligible, because you can turn on the calibration source and set it to very high luminosity, so that you have the impression that the noise has disappeared. There's always noise, of course, but the signal to noise ratio is very high in this case. And so what you see here is a set of speckles that move with time. The typical time scale, of course, it's slower here, but the typical time scale is a millisecond or a few milliseconds. It's called the coherence time of the atmosphere. And each of these speckles has a characteristic size, which is the diffraction limit. And you see that they change the shape with turbulence, but the characteristic size is always the same, basically. And of course, this is to be compared with one speckle that sets the diffraction limit. And if you integrate, if you make a long exposure, and long exposure with respect to a coherence time of few milliseconds is easy to make. Just wait for a second, for example. Well, this is the size you get for the image. That means if you have observed a source which is not resolved by the telescope, for example, a star, not a too big one, then instead of reaching the diffraction limit for the size of the point source response, you get this this big pattern, which is much larger than the diffraction limit. Of course, you've blurred your image. You've blurred your image because if you think of the image of a binary star that you could get at the diffraction limit of the telescope, with turbulence, you don't see a binary anymore. What you see is a single star, something that looks like a single star or cannot be distinguished from a single star. So this is how you lose angular resolution. You lose the advantage of using a large telescope to reach a high angular resolution thanks to the diffraction limit. So the way to go around this is now very well known since the late 80s and the early 90s. It's called the adaptive optics system, or the adaptive optics loop. It's been first developed for astronomy in my lab by Pierre Lénat and his team. So now more than 30 years ago. And the principle is very simple. The principle is that you put on the in the beam, you put what is called a deformable mirror, and you will adjust the shape of the mirror so that it exactly adopts the shape of the incoming reference, so that after reflecting on the mirror, the incoming reference will be flat. And if it's flat on on a point source, then you have recovered the full diffraction limit of the telescope. For this to work, you need to analyze the wavefront errors in real time. So you need a wavefront sensor. This wavefront sensor sends commands to the deformable mirror in real time. And if you go fast enough, that is to say, typically faster than 1 millisecond to do the full loop, then you can servo the mirror efficiently and correct for the image quality and recover the diffraction limit. You can then focus the wavefront and obtain an image at the diffraction limit. That's the miracle of adaptive optics. And it works quite well. So now the same optical simulation with real photons, but not photons coming from stars. And you see the adaptive optics system in open loop, which means it does not correct anything yet. And then you turn on the adaptive optics system, you close the loop, as we say. And of course, you obtain not several speckles, but a single speckles. Basically, all the speckles are now heading coherently at the center of the optical axis. And of course, you recover the diffraction limit. So if you observe a binary star whose separation is larger than the diffraction limit, then you indeed see two stars. You indeed see a binary star. That's this very important technique that has been used to observe the Galactic Center and to make great advances starting in the 90s and more, and especially in the early 2000s, when these systems have been available for 8-meter, 10-meter class telescopes. So you see on this animation from the UCLA group of Andrea Gaze, you see here an animation where you understand the advantage of using the adaptive optics system. And now in this 1 arcsecond field, you're not limited by turbulence anymore, but you see individual stars. And when you see individual stars around a massive compact object, then you get a possibility to measure the mass of the central object. So how do we do this? Well, there's a very simple way to, or very direct way to measure the mass of an object in astronomy, which is to measure an orbit around this object. And using the third Kepler law, you derive the mass of the central object. If the central object has a mass much larger than the mass of the orbiting point, of course, or the orbiting object, which is the case for a star with respect to a supermassive compact object. So this is what has been done by the team of Reinhold Genzel at Max Planck Institute for Extraterrestrische Physik in the early 2000s, when the NEOS system, which gave the instrument NACO, NEOS was built by a French team, Onera, MyLab, Lesia, and people in Grenoble. And NACO was equipped with an infrared wavefront sensor, which allowed to servo the wavefront and to correct for the wavefront aberrations due to the atmosphere at the Galactic Center. And then they could measure some new data points, which were very precious, because for the first time, they could measure an orbit. And so getting the orbit of a star, and that was the star called S2. You will see that S2 plays an important role in this story. Then measuring the mass of S2 gives you an estimate, the orbit of S2, sorry, gives you an estimate of the mass of say J star. But in addition to measuring this orbit with astrometry, they also did some measurement in spectroscopy to measure the radial velocity of the individual stars in the field. And by doing so, and by integrating the velocity, of course, as a function of time, you get positions. And doing so, the radial velocity gives you positions on the line of sight, and therefore you get 3D positions for each of the stars in the field. That allows you to get an even better estimate of the mass of the central object. So this is what they've been doing. And they got a first accurate estimate of the mass of Sagittarius star, which was about 4 million solar masses. As a byproduct, you also get the distance, which is on the order of 8 kiloparsecs. And on the rest of his talk, I will essentially focus on S2, which is the star with the orbit, which is most well known, and which is the one getting closer to Sagittarius A star. So that's the one which is very interesting to study Sagittarius star, and to study also the effects of Sagittarius star on this orbit, and in particular the effects of general relativity. Okay, so we know there's an object at the center of the galaxy whose mass is about 4 million solar masses. This object now has a size which is smaller than the Perrin center distance of S2 to Sagittarius star. This distance is on the order of 100 astronomical units, so basically the size of our solar system. So there's a good hint that this object is possibly a supermassive black hole. Now, during these observations with adaptive optics, the Genzel group got a very nice result. So what you see now is a series of real images. You see that they're still shivering a bit. This is due to residual aberrations from the atmosphere, tip tilt. But what you see is that Sagittarius star is blinking. It's blinking, and at the angular resolution of an 8-meter telescope, which is 60 milliarcseconds at 2 microns, it is fixed. It doesn't move with respect to S2. So this showed that probably what we're seeing here is a phenomenon very close to the event horizon, very close to the black hole, and that's also very interesting in the perspective of in the prospect of what can be done with an instrument with much higher angular resolution than a single 8-meter telescope. So this is what they observed. They observed the flux of Sagittarius star, which was blinking. Actually, there was a strong increase of the flux. The central object went from a quiet state to a very active state. For comparison, you have the star S1 just above, well, the flux of the star S1 just above. And you see the important increase in flux, factor 4, and with rapid oscillations, with a period on the order of 20 minutes. That also points toward a phenomenon occurring very near the event horizon, but with no astrometry at that time, and so there was no real possibility to fully characterize the phenomenon. But what it shows is that these phenomena exist and occur. And when we started the gravity adventure, there were 3 classes of scenarios to explain these phenomena. First of all, possibly magnetic reconnections in jets, the jets flowing from Sagittarius star. These would lead to very energetic phenomena, or hotspots at the innermost stable circular orbit, which in the case of so that's what we call the ISCO, which in the case of a Schwarzschild black hole, so a non-rotating black hole, is 3 times the size of the event horizons. These hotspots are also possibly produced by reconnection, magnetic reconnection in the accretion flow. And a third hypothesis was simply statistical fluctuations. There was another one which was Rossby wave in the disk. What is important here is that the characteristic scale of these phenomena is a few 10 microarcseconds. So the angular resolution of an 8-meter telescope at 2 micron is 60 milliarcseconds. Now we need to get down to a few tenths of microarcsecond, which is an improvement by a factor 1,000. So that was a real challenge. And to do this kind of thing, well, you need a completely different instrument. You need, since the diffraction limit is proportional to the diameter of the instrument of the of the observatory, you need, of course, to increase the diameter. And us Europeans are lucky that we have the VLT at ESO, so the same telescope that we've been using to perform adaptive optics on the Galactic Center, but we have 4 of them. And with 4 of them, you can make an interferometer. And the magic of an interferometer is that the angular resolution is not set by individual telescopes anymore, but it is set by the largest distance between these telescopes. And in the case of the VLT, the largest distance you can make is 140 meters. So there is a gain of a factor almost 20 compared to individual telescopes. Not yet a factor of 1,000, but you will see that we will use another technique to get down to this, to get up to this factor 1,000 or close to, or a few hundred. But it's already going in the right direction, on the right path. So that's the idea behind the gravity instrument. Make an interferometer with the 4 UTs. We call them the unit telescope, the UTs, the 8-meter telescopes, with the 4 UTs in parallel at the VLT to gain in angular resolution. Gravity can also use the 80s, the auxiliary telescopes, the 1.8-meter telescopes at the VLTI. You see the small, well, they look small, but they are 1.8 meter, 2-meter telescopes. This is very useful, of course, to observe stars or objects that are brighter than those you typically for which you typically use the 8-meter telescopes. Okay, so what increasing angular resolution in the infrared brings to study the Galactic Center? Well, it brings several things, several important things. First of all, for the S stars, it will allow to potentially discover new, fainter and closer S stars, closer to Sage S star. Why? Because, well, we expect theoretically to have a few more stars closer to Sage S star, and that's very important to understand their nature and their distribution. So some of the S stars are not detectable by adaptive optics because they are fainter, but also because of the confusion effect if they are too close to Sage S star. So increasing the angular resolution allows to fight the confusion effect. And the S stars are excellent targets to be used as probe for gravity near the supermassive black holes, because they are almost perfect point masses. To do this, you need to get down to a scale of a few hundred Schwarzschild radii, so a few milliarc seconds, and that's exactly the angular resolution provided by gravity. Now, for Sage S star, what does it bring? Well, it will help us to understand the nature of the flares. With the flares, it will help to probe general relativity in the very strong field regime. If we can consider the flares as point masses, which they're probably not, they are not stars. They are masses of gas in the and plasma in the accretion flow, and they will bring stronger evidence that Sage S star is a black hole, because we'll be able to explore the horizon scale. A black hole or another type of compact object, if this compact object exists. To do this, you need to reach a scale which is on the order of the Schwarzschild radius, so 10 microarc seconds or a few tenths of microarc seconds. You can do this in the infrared. You've probably heard about the you've probably heard about the Event Horizon Telescope. You can do that also in the millimeter. In the millimeter, however, you cannot access to the S stars. They are not bright enough in the millimeter wavelengths, but you can access to the accretion flow, and this has been demonstrated on M87, as you probably all know, with this fantastic image of the accretion flow around the central compact object M87. Okay, so that's a lot of good prospects. This is why we decided to build this instrument called Gravity. You have here the that's the French vision of the consortium. In red, you have the names of the members of the consortium from French labs. But of course, they are not only French members in this consortium. The consortium is led by the Max Planck Institute for Extraterrestrial Physics. The PI is Frank Eisenhower, and you have a few co-Is. The names of the co-Is and of the PI are underlined. As you will see on the map here, you have people from Germany, you have people from Portugal, you have people from France, and you have ESO. The guy with the crown is the PI, Frank Eisenhower. No Greek people yet, but I hope one day that will be the case. Would be wonderful if we could make such kind of experiment and adventure together in the ESO context. So what is gravity? So it's an interferometer, but as you're going to see, it's an instrument which is distributed all over the LTI actually, because we need many subsystems to operate the instrument and to reach the accuracy and the angular resolution that we need to study the galactic center. Being an interferometer, we have a beam combiner, which is in the interferometric beam combination lab at the center of the VLT or the VLTI, the VLT interferometer. I will not describe in detail how the VLTI works, but you have to collect the light from the telescope and then direct the light with a set of mirrors to the beam combination point. And you need to adjust the delays between these beams of light so that everything arrives in phase inside the beam combination instrument. On top of that, we have adaptive optic systems. We built 4 of them for the 4 VLTs, the 4 UTs, because we needed adaptive optic system working in the infrared, because we need to analyze the wavefront in the infrared due to the fact that the galactic center is very red because of all the dust and gas on the line of sight. And we have also a metrology system that allows us to very accurately measure the optical path lengths inside the interferometer. So from the telescope pupils down to the beam combination point. So gravity is a very complex instrument. It's the most complex instrument at the VLT. That's a general remark for interferometry in the optical domain and also in the radio. So this is why it took a bit longer to get this type of instruments compared to more classical instruments. Just a few photographs of what it looks like. This is the beam combiner. It looks like a space experiment. It's because it works in vacuum and in the cold, because we're using infrared detectors, so we need to operate at very low temperatures. The beams come from the left. Of course, the vessel here is opened, and you have several subsystems. I will not describe all of them. I just mentioned a few of them. You have the fiber coupler, which takes the beams and focuses them in single mode fibers. You have the fiber control unit, which allows to control the beams. I will show you that in a little moment. You have the acquisition camera, which is a very important feature of gravity. We have, we actually have 4 beams, so we need 4 acquisition cameras. That's why you see four sets of beams here. It allows us to identify the sources in order to accurately place the fibers. It allows us to control the pupil. It allows us to control also the metrology of the pupil, etc., etc. It's a very important feature of gravity. You have the beam combination beam combiner made of integrated optics. So to make it very short, that's single mode fibers, but inside glass. excuse me. And at the end, you have two detectors with two spectrographs, because gravity is a double field instrument. We can observe two objects at the same time, and it's very important to perform differential astrometry. Okay, we started this adventure in 2005, and we started the integration in 2013 in Garching at the MP, close to ESO. This was one day when myself and Frank Eisenhower were installing the fiber control unit inside Gravity, and as you see, we were all ready to fight COVID-19 back in 2013. So nothing very new for us, except that because of COVID-19, well, we're not very happy. We have not been able to observe, or very slightly observe, in 2020. So very few data in 2020. And we restarted to observe with Gravity at the end of 2020. We restarted to observe the Galactic Center in April, so just a few weeks ago, and then part of the observatory was shut down, has been shut down again because of the pandemic. So we should have been observing these days, but this one has been cancelled, and I hope that we will soon be able to observe again. And of course, I hope we'll all get out of this pandemic very soon. Okay, a little bit of technology here. A few things on which I have been working personally. These are fiber systems. The fiber delay lines here. We are observing two objects with Gravity simultaneously, so we need to adjust the path lengths for these two objects for each of the 4 telescopes. And one efficient way to do it is to do this by stretching the fibers, and by doing so, we could obtain optical path lengths up to 6 millimeters. Gravity is also a very accurate instrument because we need to get access to very high dynamic range, and for this we need to very precisely measure the visibilities. And one part of the secret is to be able to control polarizations to do so. And how do we do that? Well, we simply twist fibers, and by twisting fibers, as you can see on the bottom right graph, you can vary the angle of the polarization. So that allows us to very accurately align polarizations in all the arms of the interferometer. And last thing about single mode optics, the beam combiners, the integrated optics beam combiners. So we feed them with the fibers, and they are very nice also piece of glass, because they instantaneously give us the 4 samples of the fringe. We sample the fringe every 90 degrees. So we do that with these combiners. They allow us to split the light, to recombine the light, and also to introduce phase shifts of 90 degrees. And we have 24 outputs, so we have 4 telescopes giving 6 baselines, number of pairs. And for each baseline, we have 4 samples per fringe, and then we disperse these samples. That's the image you have on the left of the screen here, so that we simultaneously get all the fringe patterns, and we get instantaneously a spectrum for all the fringe patterns of Gravity in the two arms of Gravity. Okay, I could show you much more technology, but I decided to show you what we've been doing in our labs in France as an example of what we've been doing in our labs in France. I could have shown metrology. Metrology system is absolutely fantastic, done by our German colleagues, or the availability of optic systems, etc., etc. Now, the principle of the measurements with Gravity. Gravity is well, I've been an interferometrist since the early 90s. And honestly, I have always been dreaming of this type of instrument where you have sources that allow you to fight turbulence. So you feed the optic system with reference sources, and you also have reference sources to control the optical paths inside the instrument, and also to fight the effect of turbulence on the fringes, which are on the instability of the fringes. So we do the Galactic Center is a perfect field for that, because as you've seen, we have this S-star cluster. We also have these two clusters of OB and Wolf-Rayet stars, and therefore that's all these stars are in general very good reference sources for these systems to fight turbulence. So about 6 to 7 arc seconds northward from the Galactic Center, you have a source which is called IR7. Which is the source we use to servo the 4 adaptive optic systems. And in the central 2 arc seconds, we have access to stars of magnitude about 10 in the K-band, so around 2.2 microns. Here you see RS16C and RS16 Northwest. And these are perfect sources to servo the fringe tracking system. So the system that will stabilize the fringes and allow us to integrate the fringe signal, and so that will allow us to get access to very high sensitivity with the instrument. We also use these sources as reference sources for astrometry and for imaging, because they give a phase reference to apply this technique. And something we had not anticipated at all is that we also use, well, we have been using, because it's not possible anymore for the moment, SAGE-STAR as a reference source itself for S2 in imaging mode, when they were close enough that they could feed the same fiber. Their distance was less than a lambda over D of one of the 8-meter telescopes. Okay, so far so good. Just a word about interferometric astrometry. You're going to see now how we managed to make this miracle of getting to scales of on the order of a few 10 microarc seconds. The idea is the following: gravity is a two-channel instrument, so we can observe 2 fields simultaneously. We obtain in each of these fields. We obtain 6 interferograms, because we have 6 baselines with 4 telescopes. And now, if you do so, well, you can link the fringes you get for one object to the fringes you get for another object. And you see that the separation in optical path difference between these fringe patterns is exactly proportional to the angular separation between the 2 sources along the baseline of the interferometer. So if you have 6 baselines in the interferometer, you get 6 sets of fringes, and these sets of fringes are linked to 6 angular separation projected on the 6 baselines. And of course, the trick is that this difference in optical path difference is proportional to the baseline, and that gives you the sensitivity to measure the angular separation delta alpha between the 2 objects. So if you have an accuracy of 5 nanometers on the optical path difference, this accuracy is provided by the metrology system. This is where the metrology system is very important. And if you have a 100-meter baseline, which is typically the baseline we have with the VLT, then that yields and that gives you an accuracy of 10 microarc seconds on delta alpha. So this is the trick to get down to this scale, which is the size or the Schwarzschild radius of SAGE-STAR, if SAGE-STAR is a supermassive black hole. Just to give you an idea of the improvements provided by gravity, this is an example of astrometric observations performed on a double star called Gliese 65AB. We're observing this star because we plan to detect the reflex motion due to a planet around one of the stars. On the right panel, you have the history of astrometric measurement on that object before the year 2000, so the end of the 90s. You see that the error bars are quite large. The 2 graphs are the right ascension and the declination. So before the 90s, you were limited by the atmospheric turbulence. The error was on the order of a few tenths of arc seconds, or on the order of 1 arc second. once adaptive optics became available, you get down to a few tens of milliarc seconds, and with gravity you get down to a few tens of microarc seconds, and that this is the progress that is made possible by this astrometric capability of gravity. And of course, that's what we're going to use on the Galactic Center. Gravity is also an imager. When doing interferometry, if you have enough baselines, you can reconstruct images, and this is extremely important for us. On the top left, you have one of the images or one of the sequences we got when observing Sage Star during a flare event. Sage Star is actually just behind the star of Sage Star, and you see S2, which is much brighter than Sage Star. And what you see is that when the distance of S2 to Sage Star is very small, comparable to the diffraction limit of an 8-meter telescope, you hardly see Sage Star. And you not only you hardly see Sage Star, but if you measure the position of either Sage Star or S2, you are strongly biased by the confusion. And of course, by increasing the angular resolution, you completely eliminate this confusion. The image in black that you see, well, white over black that you see, are images reconstructed from the gravity interferometric observations. And now the separation is much larger than the diffraction limit of the interferometer. The diffraction limit of the interferometer is a few milliarc seconds compared to the separation, which in March 2018 was on the order of 20 milliarc seconds and on the order of 60 milliarc seconds in summer 2017. That is to say, matching the angular resolution of one single telescope. Okay, so that's what gravity is exceptional for. It allows you to completely eliminate this confusion at the Galactic Center, at least to observe the orbit of S2 around Sage Star. Okay, so fair enough for instrumentation and the principle. Now I'm going to explain 3 other results we have obtained on the Galactic Center. The first result that we have obtained was the detection of the gravitational redshift of S2 when S2 passed nearest to Sage Star in May 2018. So what we've been doing is that we've been observing both with gravity to get the position of S2 around Sage Star. And that's the images you see here, the images we constructed from gravity data with the 2 objects perfectly well separated. Even at Perrin Center, you see at the bottom right corner an image reconstructed during the passage at the Perrin Center, when the distance between Sage Star to the angular distance from Sage Star to S2 was only 4 milliarc seconds. So it would not have been resolved at all by a single 8-meter telescope. The diffraction limit of an 8-meter telescope is 60 milliarc seconds at 2.2 microns. And you see the distance between S2 to Sage Star was then 100 astronomical units, so the size of the solar system. And to the left, at the same time, we were observing with Symphony and another instrument of the VLT in order to measure radial velocity. So monitoring the helium line and the hydrogen line in order to measure the velocity of Sage Star on the line of sight. Of course, to make this kind of measurement, the gravitational redshift, you need to measure redshift, so you need also a spectroscopic, you need also a spectrograph. And what you have here is the orbit we've been, the data points we've been using to constrain the orbit of S2. So you have that to the left. We've been using the gravity data points, but gravity has been observing the Galactic Center from 2017 up to 2018 at that time. So we didn't have enough points to get a full orbit. So we used previous points observed with adaptive optics, and also by by spectral interferometry, since the period of S2 is on the order of 16 years. So gravity, of course, was not there for the previous passage to Perrin Center. And we combine the two sets of data. With, of course, with gravity having, of course, much higher accuracy than the previous instrument. You see that in the bottom right panel, where the error bars are even not visible because they are smaller than the data points. And at the top right panel, you have the radial velocity measurement from the early 2000 up to 2018. And the jump that you see around 2018 is due to the Perrin Center passage. Okay, now if you look, if we look more closely at the data, you have the radial velocity points on the top line, and the two bottom lines at the astrometry points, with the blue ones measured by gravity. So you see the increase in accuracy due to gravity. For the two bottom lines, the red line is the orbit without the general relativity precession, what we call the Schwarzschild precession. The dark line is with precession, and you see perfectly well that we were too early to detect the precession. I'll come back to that later, because that was a result that we got last year. And the top panel, you have the radial velocity with the red and dark curve, but also you have a gray curve, which is what you would expect without gravitational redshift. So the gravitational redshift is now the bump, the 200 kilometer per second bump that you see on the top right corner. Okay, so what we've done was to compare this with a model. The model was an orbit plus a spectroscopic model, and the spectroscopic model was featuring the effects of general relativity. To do so, we used what is called the parameterized post-Newtonian expansion of general relativity. Beta here is the velocity of S2 over the velocity of light. And this works as long as, of course, beta is much smaller than 1. When we did these observations, the velocity of S2 was about 2.5, 2.7% of the velocity of light. So this approximation was perfectly correct, and it works in the weak field regime. So that's the case. That was the case of S2 when it went through Perrin Center. Now, if you look at the B1 term, the B0.5 term is the Doppler shift. The B1 term is the relativistic redshift, which has two parts. The one from a special relativity called the transverse Doppler shift, and the one from general relativity, so due to gravitation. And the two have the same strength. So they contribute 50%. They each contribute 50% to the total effect. What we've done is that we have modeled the orbit of S2 around, say, J star with 15 parameters, and one of these parameters was the parameter we named F, that you see here. It's a spectral parameter. If F is equal to 1, then you have a GR orbit. If F is equal to 0, then you have a Kepler orbit. If F is equal to 0, there's no bump in the radial velocity. And fitting these data, we got a result that for F we found 0.94 with an accuracy of 0.09. So we showed that the favored theory is general relativity with a significance of a factor 10. Among the parameters that we have been measuring, we had the mass, so that yielded a new measurement of the mass with a fantastic accuracy of less than 1%, and also the distance to Sagittarius star, also with an accuracy of less than 1%. So that was the first time we could show that a star orbiting a black hole is affected by effects which are perfectly well described by general relativity with an accuracy of 10%. So that was our first result on Sagittarius star. The second result was the measurement of the relativistic precession. This occurred later, and we published this result exactly, or almost exactly, a year ago. And the effect is quite simple. This is an effect which has been very well known since the early days of general relativity, because it was one of the first evidences that one of the first successful tests of general relativity in the solar system with the orbit of Mercury. And we have been doing exactly the same, not for the orbit of Mercury, but for the orbit of S2 around Sagittarius star. And it was the first test of the kind around a supermassive black hole. So the effect, you see it here, well, the effect has been magnified by shrinking the orbit of S2 by the factor 10. The magnitude of the effect depends on the eccentricity, excuse me. It also depends on the size of the orbit. And in this case, you see the effect of this pericenter shift. It is prograde in the sense that it is in the same direction as the direction in which the star makes progress on its orbit, and it looks like it's similar to a kink each time the star goes through a pericenter. And in the case of S2, what is expected is a kink of about 12 arc minutes. So the orbit should rotate by 12 arc minutes. The expression of this kink is very well known. It is derived from the theory of general relativity, and here also with the post-Newtonian approximation. There are two effects contributing to the precession. There's the Schwarzschild precession with the parameter FSP, and there's the precession due to the spin of the black hole. So far, we have only been measuring the precession, the Schwarzschild part of the precession. The precession due to the spin is about a factor 100 smaller. So we have not been able to measure that for the moment. And you see the tiny difference that we've been able to measure. You see that the orbit does not close, actually. And you see that on the graph, on the figure to the left. And you see this the region where the orbit does not close in this little red rectangle. So that's this tiny effect that we were able to detect with gravity. Once again, you need the accuracy of gravity to make such a detection. And so we measured this FSP term, same principle as the previous measurement for the gravitational redshift. F is a parameter whose value equals 0 if Kepler is right, and equals 1 if Einstein is right. And we have measured 1.1 for this parameter with an accuracy of 0.2 or on the order of 0.2. So it's a 5 sigma, sorry, confirmation that Einstein was right. And this effect of the precession is also sensitive to mass around the black hole. So distributed mass internal to the orbit of S2. And we've been able to place an upper limit on this mass because this mass would have a counter effect. It would make the orbit precess, but not in the prograde direction, but in the retrograde direction. So we have not been able to measure this, and we have concluded that there was no mass larger than 0.1% of the mass of the black hole. you see the data point on the graph, on the two graphs below. So you have the right ascension graph and the declination graph. The blue points are the gravity points. As you see, that worked wonderfully well. And we got new points in 2020 and in 2021. The Galactic Center can be observed from the end of March until September. In 2020, the Paranal was closed, was shut down because of COVID at the end of March or the beginning of April, and so we got only one sequence of observation, very few data points. So that's why the error bars are so large, and no more point during the rest of 2020. So we could resume observations in April of this year, and then the observatory was shut down again. So we have two new points in 2020 and 2021. And as you see, so it's not a fit, it's just a comparison with the data we published in our 2020 paper. And as you see, that works perfectly well, at least within error bars, or not that much distant from the data points at the scale of the error bar for the 2020 point in declination. So this is very encouraging. We are looking forward, of course, having new point and new accurate point, much better than the 2021, than the 2020 data point, in order to refine this estimate and continue the study of potential extended mass around the black hole. Okay, now we are leaving S2 and we're going to a scale even closer to Sagittarius Star. We had been hoping for bright flares since the very first days we've been observing Sagittarius Star with gravity, and it took 2 years to get such bright flares. And we got 3 bright flares almost in a row in 2018. So that's the phenomenon I showed earlier that was measured by Reinhard Genzel and his team in 2003, except that we want to add new information to these phenomena by measuring the motion of the flares around the Sagittarius Star, if there is a motion, of course. So that's what we did. We got 3 flares in May and July 2018. I am presenting the best flare here. So as you see, we were able to measure an orbit, or we were able to measure the position of Sagittarius Star as a function of time, and it looked like an orbit. So let me comment this graph here. So you have the data points. So that's the astrometry of Sagittarius Star with respect to S2, and the central position here is so 0, 0 is defined as the median positions of the flares, and the red cross with the purple star here is the position of Sagittarius Star derived from the observations of S2. So that's the dynamic position derived from the orbit of S2 as measured by gravity. And as you see, these 2 positions, so the median position and the position derived from the S2 observations, coincide at about 1 sigma or 1 or 2 sigmas. So that's a very nice result. And the other wonderful thing is if you consider the scale of this orbit, the scale is on the order of 100 microarcsecond, and that's what you expect that's the range of scale you expect for a hotspot orbiting around the black hole close to the innermost circular orbit. We have compared our data point to general relativity simulations, and that was very fruitful, as you can see. So we used ray tracing models. We have Giotto in Paris, for example, in our team, and we could fit the data with an orbit which is 7.3 gravitational radius. Gravitational radii. The gravitational radius is gm over c squared. And in this unit, the radius of the horizon of the Schwarzschild black hole is 2 gravitational radii. So we are at about 3 times the radius of a Schwarzschild black hole, which is exactly very close to the innermost stable circular orbit, which in the case of the Schwarzschild black hole is 3 times the radius of the horizon. So when you are so close to the horizon, well, you find a speed which is very high, and as you can see, the hotspot reach a speed which is about 1/3 of the speed of light. So we are in a strongly relativistic regime here, and we are probing the innermost, the closest regions around the black hole. To date, that's the closest observation to Sagittarius star. Now you have probably noticed a detail. If you look at the green orbit that has been fitted against the data points, the orbits look a bit internal to these data points. It doesn't go through the data points. And the reason for that is that what we fit are not only space data, but space-time data. So time also matters. And what it shows is that we have a super Keplerian motion. And we can wonder why this is super Keplerian. Maybe it's because of the physics of the accretion flow. We're not in the case of a star orbiting a black hole, a star that could be assumed to be a perfect point mass. It's not a point mass at all. It's probably a region of the size of the horizon which is orbiting the black hole, and so this region is sensitive to the accretion flow. It's sensitive to the magnetic field, and this has certainly an impact on the type of orbit you can get. Or maybe that's the nature of the central object. Maybe it's not a supermassive black hole, but another type of object like a Boson star, for example. And in this case, the orbital parameters are a bit different than that of the black hole. At this stage, we don't have any mean to say which option is right, and we don't know if it will be the case one day. But we need to make progress on the astrophysical modeling of the accretion flow around Sagittarius star during these events. But as you're going to see, well, that's a very nice view that we use for our press release. It's the real data points against plotted against an MHD model of Sagittarius star, of the accretion flow around Sagittarius star. But the interest, of course, of these hotspots is that they are very close to the horizon, and so they also provide very strong tests of general relativity, and there is a very strong test of the supermassive black hole paradigm. Gravity is also able to measure the polarization. So we have a Wollaston prism and a half-wave plate that allow us to measure the Q and U Stokes parameter, so to characterize the linear polarization. And what we have measured is the following. The flare also seem to be in this QU plane, making kind of an orbit, which has the same period as the orbit in the right ascension declination plane. And this is an important fact because that points to the fact that the magnetic field is very probably poloidal and not toroidal. If it were toroidal, we would have found a period which would be half the period of the physical period of the hotspot around the black hole. And if you add to that light bending by Sagittarius star, then you get an azimuthal component that explains for the polarization, that explains the orbit-like motion around the black hole. And this is very important because as you've seen, the orbit of the hotspots looks pretty much like a circular orbit, which means that we probably see the system edge on, which is very surprising. And this is also confirmed by what we've seen with the polarization. Let's call it the polarization orbit. because to get this pattern for the orbit, you need to get an inclination on the order of 15 or 30 degrees and a distance to the black hole, which is also of 7 to 8 gravitational radii. So if you put all these constraints together and add the constraint of the contrast of the photometry during the flare, if you look at the object through the edge, if you look at the orbit through the edge, then because of lensing and of relativistic beaming, you expect that when you cross the line of nodes, where at the time when the object is pointing toward you, you will have a very strong amplification of the photometry, and this strong amplification decreases with the inclination. So in the case where there's no inclination, where you look at the system face-on, there's no beaming, there's no lensing, and therefore there's no contrast. In our case, we could place a maximum amplitude for the contrast of 2.5. So if you cross all these constraints, that points towards a value of about 7.6 gravitational radii for the orbit of the hotspot, and an inclination less than 30 degrees. So we really see an object orbiting the black hole very close to the innermost stable circular orbit, and with a very low inclination, so seen face-on, which is a bit strange, as we know that at the scale of the galaxy, we don't see the galaxy face-on, but we see the galaxy edge-on, since we are part of the disk. Okay, so that was a very surprising result in this sense. But the result is very interesting, of course, because it fully confirms that the central object is a 4 million solar mass object. If you make the assumption that this object is a black hole, and if you plot the characteristics of the orbit into a period radius diagram, as this is done here for the free flares, then what you will see is that it is exactly compatible with what you expect for either a Schwarzschild black hole, so a not rotating black hole, or a rotating black hole, even at maximum speed. So this is really an extra hint that the central object is a black hole. It, by the way, sets a new constraint on the size of the object, and the object, the mass, is inside a sphere of radius 7 to 8 gravitational radii, which is the world record to define the size of the black hole. So we are very next to the horizon, but we cannot yet absolutely ascertain that we have detected the event horizon, which would be necessary for a black hole, and we cannot yet measure the spin because the measurements are compatible with any spin for the black hole. Okay, so I'm very close to the end of my presentations. This result was very strange, and we were wondering whether we were right or not. It was very strange because of the orientation that we found, and we were lucky that at almost the same time, a few weeks later, actually, another group made an image of Sager star at 86 gigahertz at 3.5 millimeter. This is not officially this is not called the Event Horizon Telescope, but it uses the same or some of the antennas of the Event Horizon Telescope at a wavelength which is 3 times larger. And what is very interesting is that they came to the same conclusion as our conclusion. That is to say that they modeled the object, they modeled Sager star at 3.5 millimeters, and they concluded that it is consistent with either a disk or a jet at a small viewing angle of 20 degrees or less. So this is exactly in line with what we have found for gravity, and so we are very confident in our result. All in all, if you look at the recent results on the black hole, we are really living a fantastic times for black hole research. Here is a graph inspired from the work of Psaltis in 2004, where measurements are put in a graph where potential is a function of central mass. And you have here the limit of the horizon of black holes. You have the measurements made with gravitational waves on stellar mass black holes, and you have 3 points here that sample a new region of high potential and very high mass, because now we are talking about masses of few millions up to a few billions of solar masses with the event horizon and gravity. So the study of black holes and the study of general relativity in general is making great progress, and the tests are making great progress with all these instruments. And of course, it's not the end. We are just at the beginning of this new era. This led to the Nobel Prize last year in physics, both for theory and for observation. And we were very happy that our colleague Reinhard Genzel, who is part of the Gravity Consortium, Gravity is built in his team at MPE in Garching. So we were very happy that Reinhard got the Nobel Prize, and we were very proud that the gravity results contributed to this Nobel Prize. More with gravity, and that will be my conclusion. Yes, there will be more. First of all, we hope that we'll be able to measure flares again, bright flares, and if we are lucky enough, with periods less than 30 minutes, because if in this case, there's no other possibility that we see a spinning black hole. So if we have a new point here or new points here that fall on the on this green curve, we'll be able to say that the black hole is spinning, and maybe we'll even get an estimate of the spin of the black hole. Black holes seem to be very complex objects, but actually they are simple objects. They are determined by 3 parameters: the mass, the spin, and the charge. The mass, we have it. The charge, well, we can make the assumption that the charge is 0, the black hole is neutral. And so if we have the spin, then we have everything to constrain the metric around the black hole, and therefore completely describe the system. So we are essentially relying on luck. We need the right flares happening at the right moment when we are observing Sagittarius Star. We may be able to observe, to measure the spin with S2 by measuring the Schwarzschild precession and refining our estimate, but it will be very, very difficult, honestly, and unfortunately, because the amount of precession we would get from the spin would be in the maximum case on the order of 1 or 2%. So maybe we'll reach the accuracy that we need for that, but it will be very difficult. Another path is to observe other stars closer to Sagittarius Star. We have not discovered them yet, but if we do so, then we'll be able probably to measure the spin with these stars. So we are still looking for these stars. There is a good prospect that we will succeed if they exist, thanks to the Gravity Plus, which is the enhanced gravity instrument with laser guide stars and beta adaptive optics, which will allow us to improve the instrument for many reasons, but in particular to improve the sensitivity by 5 magnitudes. And this is what we need to detect and to discover stars closer to Sagittarius Star than S2 is. This is an example of what we are currently doing with gravity. You see an image reconstructed with gravity and the detection of the star S62 in the field. So you see we've reached a magnitude in K of 19 or close to 19. With another 5 magnitude, we get down to 24, and then we'll be able to see fainter stars that are completely undetectable for the moment. So if we do so, then we'll see stars with even larger relativistic effects. We'll be able to observe them on much shorter orbits and on much shorter period. and so that should leave us time to fully characterize these orbits and detect these effects and the effects due to spin. I think I'm going to stop here, and I thank you for your attention.
Thank you very much, Guy, for this very detailed presentation. It's really amazing results that we can obtain. I don't know if people have some questions. You can raise your hands or simply speak.
Am I allowed to ask a question?
Yes, Nico.
Okay, I'm a little bit confused with your statement that you can, that with respect to the innermost stable orbit, with respect to spin, your measurements so far cannot limit the spin at all. Now, it's been a very long time ago, but I remember that for a Kerr black hole, the formula for the innermost stable orbit is a very complicated one, but it has a bound, which, if I remember correctly, if I'm wrong, it's 4.5 times the Schwarzschild radius, while the spinless black hole has 3 times the Schwarzschild radius. Your measurement showed what?
Okay, so I have selected this slide, this slide here. What you see are 3 curves. That there's the red curve. The red curve is for the Schwarzschild case. The green curve is for the Kerr case with maximum spin with the maximum spin of 1. And the blue curve is for the Kerr spin, the Kerr case with a maximum spin of 1, but with a retrograde orbit. And as you see, 3 points are fully compatible with the Schwarzschild case. They are also compatible, of course, with the spin case. But none of them is incompatible with the Schwarzschild case. That's why we say we have not been able to place a constraint on the spin. The only constraint we could place would be with the blue point, which is compatible with the blue curve, meaning that in this case we would have observed a retrograde orbit in the case of maximum speed. Of maximum spin, but we cannot be certain of that.
I would have thought, if I forgot these things, but I would have thought that you would be able to eliminate a spinning black hole with a very small amount of spinning, because if I remember correctly, that 4.5 Schwarzschild radius bound goes down to 3. Which is essentially the Schwarzschild one, when the spin is very, very high. And I think it matters whether you're in the equatorial plane or not. Maybe I'm misremembering, but why couldn't you eliminate some of the spins for the Kerr case, not all of them?
Okay, that's a very good question. I honestly don't know what is this this 4.4 bound. I'm going to have.
Well, I remember my relativity course, but that was a few decades ago. So
okay.
I can find out if you are interested. I remember that the 4.5 as a bound for Kerr. I remember a very complicated formula that depends on the angles and which is the plane you look from, and that's important. That I remember, and I also remember that it collapses to the Schwarzschild case when the thing is spinning like crazy. That's what I remember. So I would have thought that there should be a region that you could explain even with what you've done already, which is beautiful work. I should tell you that.
Okay, for me, that's the, the constraint we've been thinking of is the size of the innermost stable circular orbit, because in the case of Schwarzschild, it is 3 times the radius of the black hole, the radius of the horizon. In the case of the Kerr black hole, when this size shrinks actually, and in the extreme case where the black hole is spinning with a spin parameter of 1, the innermost stable circular orbit coincides with the horizon. This is why you can get closer to the you can get to closer radii, and with smaller orbiting period, and then you are not compatible with Schwarzschild. So okay, I'm curious to see this this 4.4 or 4.5 bounds you were mentioning, because if there is a possibility to bring a constraint, that's very interesting, of course. Thank you very much.
Thank you, Nico. Is there a question from someone else? If people are thinking, maybe I could ask something. It was very interesting what you mentioned about the decoupling in the orientation between the plane, sort of like the spinning axis of the black hole and the actual axis of the galaxy, right? And this sort of like reminded me the work on other supermassive black holes, say on Centaurus A, for example, where the plane imaged by the very close, the disk very close to the supermassive black hole by the HST is completely different. It's inclined compared to the jet of the radial jet of the galaxy. So, but all in all, this the complex structures that we see around the galactic center that you already mentioned, sort of like the mini spiral, and sort of like the donut that also exists in mostly in radio and millimeter wavelengths. Would it be consistent with this orientation that you see, or what happens at the very center that gravity probes is decoupled effectively from the large motions of the gas that may feed the center?
Okay, so first of all, there's of course we find this orientation for this orbit, but we we make the assumption that if the black hole is spinning, then this is aligned with the spin, but there's no absolute certainty that it would be the case, because the Peterson-Bardeen effect that is expected to explain the fact that when you have a spinning black hole, then the disk becomes perpendicular to the spin axis. This works in some cases, but you need, I think you need to have a thick accretion flow, and this is not the case of Sage's star. So it's not absolutely sure that the orientation we have found for the orbit actually matches the orientation of the spin, but that's a possibility. Now the orientation we find is compatible with one of the remember there are two the stars which are beyond the S star cluster. These 90 massive evolved stars are locating in 2 disks, and the orientation of these 2 disks is close to the orientation we find. So does it mean there is a link? That's a different question, but that's a possibility.
Okay, thank you very much. Someone else? Well, if not, I'll ask one last question. Is it feasible to actually use gravity as is right now to look at other AGN 1068, or is it all this challenge to actually that you pointed out, you need to have a very bright star nearby to observe, and to close the loop is still a limitation that other adaptive optic systems had? Oh.
Okay, so yes, we actually have a large program for AGNs and quasars. NGC 1068 is one of them. So gravity currently works on the brightest ones. So we have a few. Well, we have 10 or 12 of these bright objects. A bit like MIDI on the VLTI as well. Mm-hmm. When MIDI used to be operated. So we have published already something on 1068, and I'm showing a result. I don't have the result for 1068 for now, but I'm showing a result we got on 3C273. So in this case, since the objects are bright enough, we don't need to have a reference star. The object is the reference itself, mm-hmm. But this is what limits the number of objects. And I mentioned the Gravity Plus instrument. With Gravity Plus, we will extend the field in which we can find a reference. We are limited with the UTs to a field of 2 arcseconds. With Gravity Plus, we will reach 30 arcseconds. So and in the same time, since we will use laser guide star adaptive optics, we will be much more efficient to correct turbulence in the case of quasars of AGN. For the moment, the stray ratio we reach is quite small. It's on the order of 10–20%. So we have a margin of a factor of 5 to 10 in sensitivity if we improve the correction thanks to laser guide stars. So the result I'm showing now, to explain it, I will go back one slide. Up. Not the right direction. Okay, sorry. Okay. I will explain the result on an X-ray binary, the principle on an X-ray binary first, which is beta crew. That's one of the first results that has been published with gravity. And what we did in this case was to measure the phase of the visibility across a line. It was well, it was bracket gamma, I think, since we're at 216. And when doing so, what you see actually is you measure the disk, and you measure across the line the location of the disk as function of redshift or blue shift, depending on which side you are. So for example, the parts of the disk that are coming towards you, towards us, they are blue shifted. Suppose the disk is rotating this way, then you will see a displacement of the object, so a phase that you will translate into a displacement to the left. And for the part of the disk that is going away from you, you will see a displacement to the right. And this is what you see here. You see the phase in degrees as a function of wavelength across the line. Sorry, not across the light and not across the night. And this phase is directly connected to a position on sky. And so this is where you see that the red part is to the left, and the right part and the blue part is to the right. And so the magnitude of the effect here gives you the size of the disk. And this is how we got a size of 20 microarcsecond in the case of this X-ray binary for the disk. So that gives you a method to measure accretion disks around compact objects. And so we use this technique to characterize the broadline region around 3C273. So we were able to do that. That gives a size for the broadline region on the order of 50 microarcsecond. But even more importantly, I would say, since you're measuring a dynamic motion, you're also measuring a dynamic mass, and that gives you the mass of the black hole. And you see that we could measure directly this time with this technique a mass of 260 million solar masses for 3C273.
Impressive.
Vasily, can I ask another one?
Yes, Nico.
I was going to ask you, would it be a fair statement that other than a black hole, something that's completely consistent with your data would be science fiction?
Well, it depends who you talk to.
I want to talk to an experimentalist, not to a theoretician.
If you talk to an
theoretician, forget it. We'll come up with 100 cases. So, from the experimentalist point of view,
yeah, the most likely assumption is that we see a black hole indeed. Absolutely.
So you cannot think of something that's reasonable other than a black hole.
Well, the only thing which could be which may be reasonable, I have a slide for that. Let me show you, is what is called a Boson Star.
Oh.
And what you see here is a simulation of a Boson Star and a Kerr black hole with Giotto by my colleague Frédéric Vincent. And as you see, they look pretty much the same. There are differences. Of course, there's no horizon in the case of the Boson Star. You can go through the Boson Star. The Boson Star is a scalar field, but that's the object that could be an alternative to a black hole. Now, you need to find a way. Well, you need to find the right boson, and because that's one of the issues. And you need to find the way to build a boson star. And we had, well, last week we had a gravity theory meeting, and we've been discussing with theoreticians. So that's and because we want to devise tests that would allow us to make the difference between a boson star and a Kerr black hole. One of these tests was published by some of my colleagues also in Meudon, was the test of the shape of the orbits, because in the case of a boson star, you could have orbits that go through the boson star, and if the boson star is spinning, then these orbits would not be ellipses or ellipse-like. The orbit of S2 is not an ellipse since it doesn't close, but it looks like pretty much an ellipse. But they would look like petals of flowers. And so I thought it was a very strong test, because we've never seen that for Sage Star, or we have not seen that yet for Sage Star. But apparently these spin boson stars would not be stable enough. So even for theoreticians, they don't think spin boson stars exist. Now there's still the possibility, if we have the right boson and if we understand how to build a boson star of 4 million solar masses, that we have a non-spinning boson star. But you see, that was a likely or a plausible alternative. And now we're reducing even the possible parameters for this alternative. So up to now, honestly, well, we know how to form black holes. We know how to form black holes of stellar size, so a few solar masses or a few tens of solar masses. Thanks to gravitational waves, we know that we have a stellar mass black holes up to 30 solar masses. We know likely scenarios to build supermassive black holes, but this is not the case for boson stars. So I think the best hypothesis so far is still the black hole, but we have to prove that there's an event horizon.
Do you have a bound on the possibility of a small net charge from the black hole that you're studying? Electric charge, Q.
Yes, I am. No, I don't have an answer for that. The usual assumption is that it is zero.
It's zero, yeah.
I forgot whether that affects at all the innermost stable.
Yes, that has an impact on the on the, since it has an impact on the, it is one of the parameters of the metric. It has an impact on the characteristics of the innermost stable circular orbit. And
So
it goes in the same direction
parameter.
as the spin. It shrinks I think it shrinks. I say I think because I have to remember, but I think it shrinks the innermost stable circular orbit.
Okay.
Well, I think we will have to stop here and thank Guy very much for this excellent talk and his time. And hopefully you will find the time to visit us in person sometime in the near future.
Thank you very much, Vasilis, and thank you very much all for your attention and your questions. Thank you for the invitation. It was a real pleasure.
Thank you. Goodbye.
Thank you. Goodbye.